Hello students, welcome back to the JEE Last Mile Preparation Series 8. Today we will take up questions 15 and 16. But before I do that, by now you already know that I'm Sujata from CBSE NEET JEEchemistry.in, and we are bringing 2 questions every day until April 4th to help students get that extra edge for their JEE chemistry exam preparation. To keep me motivated on this task, please hit the like button and don't forget to subscribe to my channel. Also, please visit my website. The link is in the description below. Let's get started. Now, we continue with physical chemistry. The 2 questions are chosen from the topic states of matter. Now, the gaseous state is a highly numerical oriented topic, and hence 2 questions are chosen from this concept or from this topic, namely the gaseous state. So here we are on question number 15. All right, let's read that question. The total pressure of a mixture of helium gas and water vapor in a vessel is 1 atmosphere. The partial pressure of water vapor is 0.3 atmospheres. At the same temperature, that is very important, at the same temperature, the vessel contents is transferred to another vessel whose volume is 1/3 that of the original vessel. What is the total pressure of the mixture in the new vessel? You are provided with 4 options. Any one of these 4 options would be the right answer. So this question will appear in section A of your exam paper. All right, let's understand this question. As you also read the question, you must have identified that you have a mixture of helium and water vapor, helium gas and water vapor. This is a mixture of 2 non-reacting gaseous systems. Helium gas is insoluble in water. So when we have a mixture of 2 non-reacting systems, we can apply Dalton's law of partial pressures. That is the first step in our discussion. So let's compile all the data and see how we can apply Dalton's law of partial pressures. All right. So let's go to the board. So we have vessel 1, the first vessel. So what is the information conveyed? So we have 2 gases. One is helium gas and we have water vapor, right? Now, the partial pressure of helium gas and the partial pressure of water vapor is found to be equal to the sum of the partial pressures of helium gas and water vapor is found to be 1 atmosphere. So this happens to be P total. All right. You are provided with the partial pressure of water vapor. What is that? 0.3 atmosphere. So you can find out the partial pressure of helium in vessel 1. So partial pressure of helium in vessel 1 would be 1 minus 0.3, 0.7 atmosphere. Okay, so let's call this as P1, the partial pressure of helium. Okay, now let the volume of this vessel be equal to V. We are not provided with any information regarding the volume, so let that be equal to V. Now let's move on to the second vessel. Okay, so now let's move on to the second vessel. You are told that the partial pressure of water vapor is 0.3 atmosphere. Okay, it will remain as 0.3 atmosphere because the temperature is maintained a constant. Okay, so there is something to understand here. Partial pressure of water vapor, okay, is found to be dependent on temperature. Obviously, as temperature increases, more and more molecules of water from the liquid state will enter into the vapor state and the vapor pressure will increase. So as temperature increases, the kinetic energy of the molecules increase, and finally the partial pressure or the vapor pressure will increase. But if temperature is maintained a constant, the partial pressure of water vapor will remain as 0.3 atmospheres. Okay, So let's see what happens to the partial pressure of helium gas. Okay, for that, so we need to find out the total pressure. Now, let the volume of this vessel be equal to 1 by 3 of the volume of the original vessel. This information has been conveyed, right? Now we need to find out the partial pressure of helium gas in vessel 2. Okay, and let's call it as P2. So partial pressure of helium in vessel 1 was called as P1. We are calling the partial pressure of helium gas in vessel 2 as P2. Okay, now you notice that temperature is maintained a constant, right? At constant temperature, the pressure, also the partial pressure of water vapor is maintained a constant. So we're not looking at partial pressure of water vapor. So what are the quantities which are changing? The partial pressure of helium will change. The volume has changed, right? The partial pressure of helium will change. The volume has changed and the temperature is maintained a constant. So which gas law will you make use of? We will make use of Boyle's law, right? According to Boyle's law, at constant temperature, P1 V1 is equal to P2 V2 for a fixed amount of gas. Okay, so now what is P1? P1 is 0.7 atmosphere into V. Remember, we are only focusing on the pressure of helium gas, and that is equal to what is the pressure of partial pressure of helium in the second vessel whose volume is 1/3 the volume. So you can cancel here the two volumes V. So what do you get here? P2 is equal to 2.1 atmosphere, 0.7 into 3. Okay, so in vessel 2, the partial pressure of helium gas is 2.1 atmosphere. The partial pressure of water vapor continues to be 0.3 atmosphere, and according to Dalton's law of partial pressures, the total pressure of a mixture of two non-reacting gaseous system will be equal to 2.4 atmosphere. So this will be the answer to this question. So let's see which option corresponds to this answer, and therefore option C is the correct answer. The answer is 2.4 atmosphere. Okay. Now let's move on to the next question. So here is question number 16. 3.2 gram of sulfur vapor at 723 Kelvin and 9.64 into 10 to the power of 4 Pascal pressure occupies a volume of 780 milliliters. The molar mass of sulfur vapor, the molar mass of sulfur vapor is to be found out. So this is a numerical value type question which will appear in section B of your exam paper. Let's compile all the data provided. Okay, so you've been provided with the mass of sulfur vapor, which is 3.2 grams. Temperature is 723 Kelvin. Pressure in Pascal is 9.64 into 10 to the power of 4, and volume is found to be 780 milliliters. Okay, the moment you compile this data, you will know which formula has to be applied here. It's a gas, so we have to apply the kinetic gas, the ideal gas equation, ideal gas equation or the combined gas equation. All right, so let's write down that formula and substitute. So here we have the formula PV is equal to nRT, correct? So N is equal to PV by RT. We need to find out the molar mass. N is equal to mass over molar mass, that is equal to PV by RT. And now let's write down the formula to get molar mass. So molar mass is equal to mass into the universal gas constant R into the absolute temperature divided by pressure into volume. Okay. Let's go back to the question. Here, the pressure is in Pascal. When the pressure is in Pascal, the volume has to be in meter cubed, right? This has to be converted to cubic meter, which is 780 into 10 to the power of minus 6 cubic meter. If the pressure is in kilopascal, if pressure is in kilopascal, then the volume has to be in liters. So just make sure that the units are correctly substituted. So let's go back to our formula. Okay. Now let's substitute all the quantities. So what are the quantities here? The mass is 3.2 grams into R 8.31 into 723 divided by, you have the pressure as 9.64 into 10 to the power of 4 into 780 into 10 to the power of minus 6. Okay. Now this involves a lot of numbers. So let's round off certain numbers to make the calculation simpler. So let's convert the 3.2 to 32 into 10 to the power of minus 1. 8.31, let us make it 8 into 723 divided by 964 into 10 to the power of minus 2 into 10 to the power of 4. So I've made this into a whole number into 780 into 10 to the power of minus 6. So let me compile all the numbers here. 32 into 8 into 723 divided by 964 into 780 into 10 to the power of 3. So if you look at 10 to the power of minus 1, 10 to the power of minus 2, 10 to the power of 4, and 10 to the power of minus 6, on the numerator you have 1000, 10 to the power of 3. Okay. So now let's divide these numbers by 2. So 2 4s are 8, and this becomes 2 4s are 8, 2 8s are 16, 482. Again 2 2s are 4, and this becomes 241. 723 by 780 is 1.0 something. So let's leave it as 1. So now what do you have? You have 32 into 2, which is 64 into 1000 divided by 241. And that is equal to 64,000 divided by 241. Okay. And this, if you divide by 241, it is 2 and 65, approximately 265 grams per mole. So this will be the molar mass of sulfur vapor. Okay. So let the formula of sulfur vapor be Sx. All right. So which allotropic form of sulfur would that be? How many atoms would be there in that sulfur molecule? You know that sulfur contains multiple atoms, right? So let's see how many atoms are there. Now we know the atomic mass of sulfur, which is, molar mass of Sx is equal to 265, all right? And here we have 32 into x is equal to 265. X is equal to 265 by 32, and that will be 8.2 something. Let's leave it as 8. Okay, because we have definitely rounded off a few numbers before, so the approximation would be 8. So 8 will be the number of atoms present in that sulfur molecule. So what is the formula? Let's go back to the question. The molar mass of, they've asked only for the molar mass. The molar mass happens to be 265 approximately, and the formula is S8. 8 atoms in that molecule of sulfur. Okay, so these were 2 concepts chosen from that chapter, which involves many more concepts. So if you found today's video useful, please hit the like button and don't forget to subscribe to my channel. Also visit my website. The link is in the description below. See you tomorrow.